or I just put less light. Yeah. So if bases are like this, the sugar phosphate backbone will be perpendicular to it. So if the bases are like this, the sugar phosphate backbone will go puncturing your computer screen. Got my point? Sugar phosphate, if the bases are parallel to the computer screen, sugar phosphate backbone will go penetrating your computer screen. I don't think so that is good enough because you have to pay 30,000 to damage your computer. Got my point?
Yes, sir.
Okay. If that happens, then so this okay, when I am displaying the slide, you can see my hands also. I think it is coming short, I guess. Yes or no?
Yes, sir. Yes, sir.
Okay, okay, fine. So these are the two bases, and at this point they are attached to the backbone which is going penetrating your computer screen. The distance between these 2 points is 10.85 angstrom, and the distance here you see of the total hydrogen bond is 2.81 angstrom. And if you can remember our previous class, we told that the covalent bond distance is 1 angstrom, and the hydrogen bond distance between and the distance between hydrogen and the hydrogen bond acceptor is 1.8 angstrom. And you see how nicely that has fit over here. All these are in the range of 2.8, 2.9 angstrom. So perfect hydrogen bonds, and all of them are straight lines. Okay, got my point? So we go to the next slide. Okay. Okay, next is the always, as I was telling, the base pairs are perpendicular to the backbone. Bases are mostly hydrophobic, need to minimize solvent exposure, and that is why bases get stacked against each other, one on the top of other. And as they stack against each other, what happens that again the previous class we told that bases can have two forms, keto form and enol form. In the physiological pH, all DNA bases are there in the keto form, but in chemistry there is nothing called 100%. There's a tiny fraction of the bases which is there in enol form also. We call this keto enol tautomerism, and the bases have some aromatic character. What is aromatic character? Whenever you get a double bond, you will realize that there are pi electrons involved. This pi electron, suppose this is the base. This is my hand is a base. Say thymine. In thymine base, on the top of the thymine and the bottom of the thymine, you have the electron clouds of pi electrons coming up and coming down, and they form this kind of aromatic clouds. So when one base comes and sits over the other, this pi electron from one base can have or can enjoy the pi electron area of the top base also, the base just sitting above it, and that gives the stabilization, and this stabilization we call DNA base stacking. So bases in the DNA have also alternative single and double bonds. They also have pi orbitals. Pi orbitals of adjacent bases, base pair can overlap, and that creates greater freedom of movement of the electron. Greater freedom of the movement gives greater stability by laws of entropy. And that is why DNA base stacking is a very stabilizing interaction. So did you get the point? Is it okay? Yes or no?
Yes, sir.
Yes,
Okay,
sir.
fine. Okay, now one more very important thing. So suppose you have a ladder in house. In the ladder also you have two bamboo poles. Okay, and there are foot plates in the ladder, which by that you can climb up the hill or up some obstacle or on the top of Almira. But the trouble is that DNA is also a ladder, correct? A sort of a ladder, where two phosphate backbones are going like this, and perpendicular to it you have the steps. But we also told that one laddered step is just on the top of the other, that gives base stacking. This is what we have discussed so far. But had been the case Is it possible to get a twisted DNA structure like what we know? DNA could have been there like a ladder with two backbones going like this and bases like this. It is like simple, what is called in Bengali, we call it moi. Hindi, I don't know. In English is ladder, just like a ladder. But we know that DNA is not like that. DNA is twisted. Correct. So how come this twisted nature will come? Taking into consideration that bases are stacked against each other. Any suggestion? You have to twist it. Then how can you twist it when I told that it is like a ladder? Have you seen a twisted ladder?
Yes, sir.
In the twisted ladder, how the steps are located, arranged? They are like this, little bit twisted against one another. If I can show you a picture of a twisted ladder. Simply like this, almost like a DNA. So you see here the steps are not parallel but little bit at an angle against each other. We call these as twist. In DNA also we have this kind of a twist between two base pair, two adjacent base pair. This property is called twist. Let me come to the actual picture of DNA. Yes. So if these are the two DNA bases, they are not like exactly one on the top of the other. They are twisted by an angle of 30 degrees. So if it is two bases are like this, if they are properly on the top of each other, it is not possible to have a DNA double strand which is twisted. So what happens that these two bases takes an angle of 30 degrees. So in each base pair on the top of each other, the superphosphate backbone can take a little bit twist against each other. So per base pair the twist is 30 degrees. So for a 360 degree twist, how many base pair we require? Simple, 360 by 30, how much it is? 12, correct? In DNA, the DNA pitch of bDNA is 10.5. But to get a full 360 rotation, how many base pairs are required? Just now we found 360 by 30 equal to 12. So there is some anomaly, correct? So in using a 30 degree twist, you cannot can get a full 360 degree rotation. So what is the actual measurement? The actual measurement is, it is not 30 degree, it is 34.3 degrees twist. So each base is twisted against each other by 34.3 degrees. So if 34.3 is there, so 34.3 into 10.5, how much it is? 34.3 into 10 is 343 plus 15, 8, 360 degrees. So these bases are tilted against each other by an angle of 34.3 degrees. The axial rise between each of the bases is 3.4 angstrom. The helix pitch is 35.7 angstrom. But that is not all. That is not all. There are still parameters, still very important parameters by which these DNA bases differs from perfect stacking against each other. Twist is just one part of the story. Other than that also, DNA bases does two more very important type of rotation. One of the rotation is called tilt. And what is tilt? You told somebody, if you tell you that your car is tilted while parking, what has actually happened? One end of the car is down, one end of the car is on the top, on a little bit up, correct? Exactly same thing is happening over here. Look at this tilt figure here. In the tilt, what happens that one base pair just get tilted by the side of the sugar phosphate backbone. So these are the sugar phosphate backbone. Look at my hand. Okay, these are the two bases. So by the axis, by this axis, so towards the sugar phosphate backbone, one base is little bit tilted compared to the other. And what is this tilt angle for BDNA? This tilt angle is minus 6 degrees. Other than tilt angle, they have one more angle, that is roll. And how roll is defined? Roll is defined as this angle, which is perpendicular to the tilt angle. So roll has nothing, not much role to play, but tilt is very important. And other than these two, there is twist and tilt and roll. There is another parameter which is called propeller twist, where these two bases which form the base pair, they twist against each other, which is called propeller twist. That is also not a very important parameter. So important parameters are twist and tilt. Why they are important? They are important because in the three form of DNA, as you see, their twist and tilt value differs. In case of BDNA, what was the twist angle? Twist angle is almost just 34.3 degrees. This value will be, you may get little bit different if you, when you read various textbooks. Some will tell 34.3, some will tell 35, some 36. Nothing to worry. It is little bit here and there, plus minus. All are experimental parameters, so small 5% deviation is tolerable. But what is important is the concept. The concept that one base pair is little bit shifted compared to the other base pair. So in case of BDNA, we have base pair twist. Right? Twist angle is 36 degree. ADNA it is 33 degree. ZDNA is minus 30 degree. In case of tilt, in BDNA we have the tilt minus 6 degrees. ADNA is 20 degrees and ZDNA is plus 7 degrees. So that is why twist and tilt are very important parameters. Based on these parameters, we can tell what form of DNA we are talking about, whether it is A form of DNA, B form of DNA, and Z form of DNA. So other than that, what you knew about these DNA forms, that is two of them are right-handed, that is A and B DNA, and Z DNA is left-handed, you know that there are other parameters now which differs one of these DNA forms from the other two DNA forms. So did you get the point? Did you get the point about these finer details of DNA parameters, twist, tilt, and what? Twist and tilt. Roll is not that important. Propeller twist is also not that important. But did you understood twist and tilt? Because these two are very important parameters. Do you have any confusion? Is it okay?
Yes, sir.
What I recommend, you have the